Okay. Hi, everyone. Sorry that I cannot attend in live. Hope that I can communicate well via Zoom. And if you have any further question, I will be happy to answer them on Slack, on mail, or whatever. Okay.
Brit, you are not in the slideshow mode. Yeah.
Okay, that's okay now? Yeah. Okay. So I'm gonna present a new idea. This is actually a vision paper, but I'm gonna give you some concrete result that we have so far. And this is a collaboration with Micah Farella from MIT and Babak Salimi from San Diego, and Anna Zhang, which is a PhD student at MIT. Okay. So I'm going to start with some motivation. Why do we need those causal data integration? And the main theme is related to what we hear so far today is about explanation. We want to explain a query result. So I'm going to start with explanation of correlation, and then I'm going to talk briefly about causal explanation and why we really want causal explanation. And then I'm going to focus on the causal data integration motivated by the causal explanation, why we need this a new line of research. So we talked about SQL queries, and I'm going to focus on aggregate SQL queries, which can be seen as a way to expose correlation in the data. And this is based on a recent work with Michael Farella and Yuval Moskovich and Babak Salimi. And the idea is that we want to understand unexpected correlation observed in user query, but in many cases, it's the only reason that we're seeing those unexpected correlation is because of confounding bias. That means that there are other factors that affecting the result, and the only reason that we see two variables that changes together is because there are other variables that can explain it. So I'm gonna give you a nice example that I like to share. And this is a real life example. And this is based on a study that looks on that data of people asking for parole, and they went to court, and and then they look on the parole and the time of the day and the decision made by the judges. And then the authors of this paper look at the data set, and they concluded that closer to noontime, when the judges are hungry, the probability of the decision to be rejected are higher. So the natural conclusion of them is that hungry judges, when they're hungry, are tougher, and you don't want to get to a parole near noon. So this is a correlation they saw in the data between the probability, time of the day, and the probability of the decision to be rejected. And then a few months later, another group of authors look at the same exact data set, and they discover that the only reason that they saw this correlation is because there are other factors that they did not consider. Like the order that people come to the court, it's not random. People arrive to the court by different jails in different time of day. People that have lawyer usually come early in the morning, and et cetera, et cetera. And if you take those confounding variables into account, you actually discover there is no correlation at all between the time of the day and the probability of the parole to be denied. And of course, there is everyone expects that the first paper is highly cited. Everyone thinks that hungry judges are tougher, but no one really talks about the second paper that reveals that there is actually no correlation at all. So the takeaway of this story is that we have to keep in mind that we want to explain some correlation. We have to ask ourselves, maybe there is another way to explain the correlation that we're seeing through an unobserved variable that can completely explain the relationship. So back to SQL, let's consider a flight dataset that we have. Flights operate in the US by large airline carrier, and we see on the left side an aggregate SQL query that simply computes the average departure delay grouped by city. And we can see there is a big difference between cities. And the natural question is, why does the choice of the departure city has such a strong effect on the departure delay? So again, it can be seen like a correlation between the city and the average day, and we want to try to explain what explains this correlation that we see in the data. So we call the departure city, in this case, I'm going to call it the treatment, and the departure delay is the outcome. and we want to explain the connection between those two variables in the dataset. But our key observation is that in many real-life scenarios, and in this scenario as well, important variables might be missing from the data. And in this example, weather-related variables like the temperature, the visibility, or airport traffic, like that can be that can be approximated by, for example, the population density and size, are missing from the data, and maybe those kinds of variables can completely explain the relationship between departure city and departure delay. So there is a lot of work, and also Benny and Daniel Amir talked about, there is a lot of work about explaining the result of of SQL query, and those work all look on the input data, try to explain the result. And what we wanted to do in this paper is not looking only on the input data, but also look on external data sources like knowledge graph or data lakes or any web table, anything that can be related, maybe can give us a hint on to explain the unexpected correlation seen in the data. So at a very high level, what we did, we automatically mine unobserved variables only from knowledge graph in this work. And then after getting hundreds of maybe relevant, maybe not relevant variables, we enrich datasets, then the main goal was to identify only a small subset of variables that explain the correlation that we see in the query. So more formally, we were given a set of candidate attributes from the input dataset or attribute that we extracted from related data sources, and then we want to find a subset of attribute that minimizes the conditional mutual information between the treatment and the outcome. In this case, is the departure delay in the departure city. I'm going to skip on the algorithm. If you want to hear more about the algorithm, I can do it offline. But continue with our example. So for this query, the explanation that we find was the set of three variables, which is the population size, which is a proxy for the air traffic. The bigger the city, the bigger the population, we get more air traffic. The year law Fahrenheit, which is again some attribute to describe the weather in the city, and the airline carrier. And intuitively, that means that in a city that are at the same size, that have a similar weather condition, and if you're using the same airline, you are expected to get the same departure delay. It's not a full explanation. Cannot fully explain the correlation because there are other unobserved variables, like, for example, security or unexpected event, but those variables explain most of the unexpected correlation seen in the data. Okay, so the main issue with what I told you so far is that we were focusing on correlation, and we wanted to explain the correlation, and I talked about confounding bias, but we actually had no assumption on any causal relationship. And of course, if I want to just predict the departure delay, a good way to predict the departure delay is look at the arrival delay. So of course, if the flight departure late, the arrival delay most likely will also, I will also experience a arrival delay of course, of the same flight, but it doesn't mean that the arrival delay has a causal relationship to departure delay. So in order to really draw causal conclusion, we have to have some causal reasoning about the attribute that we are considering beyond just observing the correlation in the data. So in an ongoing project with Micah Farella and Amir Gilad and Sudeepa, and this is still under submission, we're looking for causal explanation. Instead of just explaining the correlation, we actually want to draw causal conclusion from the data. So example question that we want to answer is, what are the factors that influence the salaries of developers in different countries? Or what are the factors that affecting the departure delay in different cities? And in order to answer those kinds of questions, we have to be able to quantify the effect. So for example, we have to be able to quantify the effect of how much that having a master degree impact the salary of a developer in the US. So our overreaching goal is, given a data set and some a group by average query, we want to explain the view by causal explanation, a set of causal explanation. So for example, looking at this data set and this query, an example explanation for a subset of tuples in the query result, in this case are countries around the world, is to say that for countries in Europe, being individual under the age of 55 with a master degree positively affects the salary. In this case, on average, their salary is higher by 36K. But on the other hand, being a student has a strong negative effect on the salary. In this case, if you're a student, your salary will be 39K minus the average salary in countries of Europe. So more formally, what we want to say that given a data set and a group by query, a number K and a threshold, we want to find a set of explanation that has no more than individual K explanation. We want to explain at least a theta fraction of the tuples in the query answer with no redundancies. And intuitively, we want to make sure that the overall explainability is maximized. And when I'm saying overall explainability, I'm talking about the causal effect that we are reporting. We want to find those treatments, those intervention that causes the highest impact on the outcome. If it's the departure delay or the salary, we want to find what really changes it to be, what really causing it to be high or low. So let's just focus on one specific causal question that we want to answer. How much does choice of an airline carrier affects the flight departure delay? And to be able to answer that, we are adopting a Pearl model for a causal for causality on observational data. So I'm just going to briefly talk about how we can do it, and then I'm going to talk, and then I'm going to move on to the causal data integration and why we need a causal data integration. So let's assume that I want to compute the effect of American Airlines and United Airlines, their choice of this airline carrier on the departure delay. So hypothetically, what I can do for every flight, I could randomly decide if this flight will be operated by United Airlines or by American Airline, and then I can measure what is the average delay and report which one of the airline has a longer average delay. But of course, you can't really do it. But we can use randomized experiment. So in a randomized experiment, what I wanted to do, because I can only observe one airline carrier for each one of the flight, I want to say that if I can randomly assign either American Airline or United Airlines, I will randomly assign that, and then I will measure the average delay, the expected average day, and this will be the average treatment, the average treatment effect, which is the causal effect that I want to measure. But as I just said, we can't really do it in practice in many scenarios. So instead, we are using Pearl model for inferring causal effect over observational data. And in which case, what we want to measure is the average delay of using American Airline or United Airline when we are taking into account all the confounding variable. And I need to know, in order to answer that, I need to know what is the set of confounding variable that I need to take into account. And this is the variable Z here. It could be the weather condition, it could be the security delay, or any other variable that can affect it. And this is the main question, that how can we know what is this set of confounding variable that we need to account to? So in order to answer this question, what we need is, in Pearl model, we need a causal DAG that describes the causal relationship between the variable that we have in our data set, and then we can identify the sufficient set of variables to account for in order to answer a causal question. So in theory, to provide a causal explanation, what we need is a data set with the treatment and the outcome, and we need this a causal DAG, and then we can identify a sufficient adjustment set, and then we can, using Pearl model, we can compute the causal effect that we need to provide a causal explanation. But what we have in practice is some kind of incomplete data set, it could be with a lot of missing variables and no causal DAG at all. So the purpose of causal data integration is to bridge this gap of, we want to be able to answer a causal question, but we have an incomplete view of the world and no causal DAG. And to get to this causal DAG and this complete data set, we can do it manually, but it takes a lot of time and effort. And what we offer with the causal data integration is an automatic tool to do those two steps at the same time. So there are many challenges in order to achieve this vision. And the first challenge is the completeness. We want to make sure that all the relevant variable will be included in our dataset. We don't want to miss some relevant variable because we already talked about the confounding bias. So we want to make sure that the completeness, every relevant variable is observed, will be included in the dataset. The second challenge is the robustness. We need to handle many data issues because we're going to join our input table with multiple variables from different sources. So it could be that we're going to have many missing values or outliers or some wrong values or a complex dependency, like one-to-many relations or many-to relations, and we need one table with all the variables. So we need a principal way to handle those issues to ensure that the causal inference is reliable. And the third challenge is the conciseness. So every mistake that I'm going to do in the causal DAG can affect my causal estimation. And a common way to achieve this causal DAG is to use, there is tons of existing causal discovery algorithm. So I can use this off-the-shelf causal discovery algorithm or even ChatGPT or any other algorithm that can provide us the causal DAG. But now we want to verify that this DAG is correct and aligned with our domain knowledge. But if I have too many variables and the DAG is too big, I cannot manually inspect the DAG and make sure the DAG is correct. So I'm going to give a few more details about each one of the challenges. So for the completeness, let's assume that this is the data set that we start with, and this is actually a projection of the flight data set. And I can extract multiple variables. So without any additional variable, I can look at the data set and I can wrongly come to the conclusion that American Airlines has a strong effect on the departure delay because all flight operated by American Airlines has a bigger departure delay compared to the other airline carrier. And then I can join this table with multiple other variables to see if I can explain this correlation. Maybe there are other unobserved confounding variables that can explain the correlation. So one example is maybe the departure dates. Maybe those flights that I'm looking at for American Airlines operate around Christmas time, which it is well known that around this time of year, passenger experience longer delay. So this is an example of one variable that can be extracted and joined to the table. Another variable is the passenger sentiment. Maybe all the passengers that travel with American Airlines reported low sentiment. And even though this variable is highly correlated with the outcome and the treatment, we need to see that correlation, it's not enough to make sure that this variable is relevant to join to our table because there is no causal relationship here. Most likely that the passenger sentiment was measured only after the departure delay, only after the flight. So therefore, this is not a relevant variable to include in our data set because we only want to include those variables that are relevant to the causal estimation. In this case, this variable is not relevant. So that means that when joining the variable, we need to make sure that first we want to know that what is the source of the variable that we are joining, and maybe to this source we can assign some probabilistic to see what is how sure are that those values are correct or not correct, and also how the extractor operates. And this will give us some hint, or maybe this variable measured only after the flight operates, and then we can assume that there is a causal relationship between the departure delay to the passenger sentiment and not the other way around. Another variable could be the weather condition. In this case, assume that all the flight operate under American Airlines was operated either under heavy snow or thunderstorm, and this can completely explain why those flights had experienced a longer departure delay. Okay, so for the second challenge, the robustness, and this is an active ongoing research with Anna Fahira and Yuval Moskovich that we are currently looking at. And we want to resolve data issue that can affect a causal estimation. And we are arguing that existing tool might be not enough to deal with causal inference. And the main reason behind that is that causal conclusion compared with, for example, prediction are more sensitive to data issues. So one example is the selection bias, and selection bias can occur when we see that we try to come up with a conclusion that observed on non-representative portion of the population. So if we want to estimate a causal effect over non-representative population, of course, we can end up with a wrong conclusion. So assume that for this data set, now I have the weather conclusion, the weather condition column, but I only observe the weather condition for American Airlines for heavy snow and thunderstorm. And I don't have the weather condition for any other flight.
So you have about 5 minutes left, okay?
Sure. So one way to deal, thank you, Sadipa. One way to deal with missing value is just to drop all the missing value or try to impute the missing value based on the observed value. But here, if the missing mechanism is unknown, we can actually draw wrong conclusion. And here, for example, the missing mechanism could be that I only observe the weather condition if the weather condition were extreme. So all the null values are actually should be completed with clear weather. So this requires some dedicated solution to handle with data issue if the task in hand is causal inference. And I'm going to move next to the last challenge about the conciseness. So as I mentioned, the causal DAG might be incorrect, and we want to enable this causal DAG to be manually verified. So an idea is to let's summarize the DAG. And this is another ongoing research with Anna Zhang, Micah Farrell, and Babak Salimi. And the main idea is that we want to summarize this causal DAG. And intuitively, I'm just going to give you the high-level idea that what we're trying to do, we want to make sure that the input causal DAG will be summarized to have no more than k nodes. We want to make sure that only semantically relevant nodes are merged together. And we want to make sure that we retain the maximum amount of causal information. And the way we do it, we want to make sure that all the conditional independence, which is data properties that are encoded in this causal DAG, are recoverable from this summarized causal DAG. And there is a lot of computational challenge in order to achieve this goal because the number of such conditional independencies is exponential. So how can we even count it? And because we summarize the DAG, we need to define a new way how to read off the summarized DAG all the conditional independences it implies. Okay, so to summarize, as I said, in order to answer a causal question, we need to have this single and complete relational database and a correct causal DAG, but we start with incomplete dataset with no causal DAG, and this is when causal data integration might be useful. And intuitively, what we're doing, so the knowledge extractor, this is a way that we want to extract all the relevant possibly relevant variables from data lakes, from knowledge graph, or for any other data source to address the completeness challenge. The data organizer, this is the model that wants to edit wants to account to the robustness challenge. And then we have the summary causal DAG builder in order to build this summarized causal DAG, which will be easier to work with. So to summarize, in this talk, I introduced the causal data integration, which is a new research direction to mine and organize data for causal inference. Unlike conventional data integration, we need to curate only causally relevant variables, not any correlated variable as we show, not any correlated variable is relevant here. And also, we want to make sure that the end causal DAG will be interpretable and concise to enable a reliable causal inference. There are many other open problems, like how to extract relevant and interpretable variables from text, from images, from log data, how to deal with complex dependencies or probabilistic data, and how to bridge the gap between a scenario when we see that we have some gaps between our data and our domain knowledge. And this is just a handful of examples of open problems that are still needs to be accounted. Thank you very much for listening. And if you have any question, I will be happy to answer any question in the open discussion that we have or via email.
Question for Brit.
Hi, Brit. Nice talk. So I have a question about the causal DAG finding. So now that we have like LLM-like models, and often the data properties are semantically meaningful, like airline delay and stuff like that. So do you anticipate that LLM could help us find this causal DAG or something along that line?
Hi, thank you, Anna. Yeah, thank you so much for the question. So maybe it wasn't clear for the causal DAG. First of all, you are right. LLMs might be very, very useful. And in our demonstration, we actually use the LLM to try to understand the similarity between the nodes and also to get some topic for the nodes that we cluster together. And they were very useful. In terms of inferring the causal relationship between two variables, we found those LLMs not to be enough. There is another paper that I can share with you that saw the same phenomena. And the main idea is that those causal DAG cannot distinguish between direct effect and indirect effect. If you ask him if something is the cause of something, they cannot distinguish between is it direct cause or is it indirect cause. So relying only on large language model to build this causal DAG might be not enough. But the focus of our research is not to build a causal DAG, because this is a completely different line of research for causal discovery. And we're assuming that we have some black box to build this causal DAG. It could be using large language model or any other causal discovery algorithm. And we focus on the task of graph summarization. But answering to your question, and this is something that we actually saw in real life data. Sometimes you get this causal discovery algorithm that tells you, oh, there is a causal relationship between variable X and variable Y, but it doesn't align with your domain knowledge or with what you get from ChatGPT. And then the main question is, what do you do with it? How can you align between your domain knowledge or between large language model and what we see in the data? Maybe the data is wrong. Maybe you have a selection bias, or maybe the large language model give you indirect causal relationship. And I don't have the answer what to do in this case, but I think that this is a fascinating direction for future work, how we can answer that. And I will be happy to talk with you about it offline.
Okay, so let's move on to the discussion session. We will spend maybe 10-15 minutes to see to